So I look around at the boards for each table, and it appears that there doesn't seem to be any controversy on the first two. Everybody has false and true, but there is a problem with number 3. One group said true, and 3 other groups said false. So let's take a look at number 3. One of the things that you have to remember in algebra and arithmetic, for that matter, is that you have to keep straight what you do with addition and subtraction and what you do with multiplication and division, because the rules don't apply to all 4 operations. Anytime you're asked to add and subtract something in mathematics, you have to add and subtract things that look like the same. And the way you add and subtract them is you say, how many of each of these things do I have? And then you put them together depending on the operation. So when you look at this, this is addition. And the 2 things that you're adding have an identity. The identity is called the square root of 2. And since they both are square roots of 2, their identity stays the same. It's asking, how many square roots of 2 do I have? And it says I have 21 of these things called square root of 2, and I have 10 of these things called square root of 2. So what you have left is 31 square roots of 2. You don't end up with square root of 4 because you could only do that if there was a multiplication sign there. Okay, so try to separate out whether they're radicals or exponent problems, what you do with adding and subtracting and what you do with multiplication and division. 2 totally different stories in mathematics. So when we come down, let's move right down to number 8 quickly. Number 8, you have 2 radicals as well. Some people start working on the square root of 50 to try to simplify it. The way this is broken up isn't very helpful. And when you find that, you can still arrive at the same answer by simplifying this. But it's much easier to just say, I want to start all over. And notice you have a square root sign here times another square root, which means you can call that the square root of 50 times 6, all under one radical. And just start fresh with the square root of 300. Because the minute you look at the square root of 300, you say, I know that 100 divides into 300. 100 is a perfect square, so I can rewrite this like this. The square root of 100 times the square root of 3, which is 10 square roots of 3, which is exactly what we have there. Now, if you started off trying to simplify each one of these, it's a little harder, but you can still get to the same answer. Let me show you. It's just a pain in the butt. That's why I suggest going back to the original number. This is the square root of 25 times the square root of 2. This is the square root of 6. So the square root of 25 is the only perfect square there. You can call that 5. Now you have to smush these guys together to get the square root of 12. And now you can break the square root of 12 up into the square root of 4 times the square root of 3, which is 5 times 2 square roots of 3, which is 10 square roots of 3. That's a lot of work. Versus just saying, I have a multiplication problem. This radical, if this was addition, you couldn't touch it. But with multiplication and division, you can rewrite it under one radical. Because a radical represents a square root, which is the same as an exponent problem. Because this could be written as 50 to the 1/2 times 6 to the 1/2. So you can apply that 1/2 to both of these, which is the same as applying the square root of the 1/2 power to 300. So 2, 3, and 8 are good to look at and differentiate in your mind what you're doing and why you can do one thing versus another. 4 is one of the bugaboos of all math teachers. It's false, but it's false because this is what you confuse. You confuse your exponent properties, which don't apply here because you have a big fat subtraction problem there. Your multiplication problems only apply to multiplication, excuse me, I meant to say your exponent properties. Your exponent properties only apply to products, which is multiplication problems, and division. Every division problem can be turned into a multiplication problem. Why? Exponents tell you about the number of factors. So it only applies to, the properties only apply to multiplication and division. You have subtraction in here. So if you want to apply this exponent, you have to write out what it means to square something. And now you're looking at 2 binomials. Binomial means 2 terms. And you have to use the distributive property on this twice, what you call FOIL, to end up with 6x to the fourth minus 8x squared plus 1. Okay? Huh? -1 times -1 is 1. Yep. The last one down here? It is true. But can we wait till we get there? Okay. Any questions on this one? So if you wrote false and you wrote 16x to the fourth plus 1, you're applying the exponent property when you shouldn't be applying the exponent property. So make a note for yourself, okay, that this is subtraction. Okay, well, let's take a look at this. Let's start really fresh here. We got 4x squared minus 1, the whole thing squared. The first thing you say is, I'm not falling into the trap and thinking I square each one of these because I have subtraction or addition. So that's the first thing you need to clarify. So you're just applying what it means to square something, which means you have two identical factors that you're multiplying. So you do 14x squared times 14x squared, which is 16x to the fourth. You have your middle term, which is negative 4x squared. You have your outer term, which is another negative 4x squared. And then you have your last terms, -1 times -1, which is plus 1. These two you can combine because they're like. So you get 16x to the fourth. Negative 4x squares and another negative 4x squares is negative 8x squared plus 1. Okay, any questions on that? All right, so let's take a look at what number are we on now? We are on 5. Everybody has true for 5 that I can see, so no questions there. 6 is false. Sure. So this is a division problem. So since it's all factors, meaning it's all multiplication all the way across, you can separate these just like this, as 3 individual fractions with multiplication. And you do the division that each one suggests. 24 divided by -2 is -12. X squared divided by x to the fifth, when you divide, what do you do to the exponents? You subtract, so that's x to the -3. And I'll get to your answer in a second. And here you subtract 13, take away a -2, which becomes +2, which is y to the 15. You never leave negative exponents in your answer. Right now, this x is in the numerator, and because the exponent is negative, you say, oops, you got to change your position. You go downstairs. You've been a bad little exponent. You're going downstairs. Okay? Does that answer your question? Okay. F, there's a lot of problems with F. Most people remember in their group that anything except for 0 to the 0 power is 1, but then they have a problem with that. This is 1/4, and when you subtract 1/4 from 1, we'll get 3/4. I'll go over rational exponents in the teaching demo in 1 minute. True on number 7, and it seems to be true across the board. Number 8 is true, and number 8 is not finished by a couple of groups. Okay, so number 8, what kind of problem do we have? Now, when I ask you that, it would be the very last operation you would do. You could absolutely drop these parentheses right here on the 3x plus 5 with no problem. And then, could you just drop these parentheses and leave it just like it is, 4x take away 7? No, because it's saying subtract each one of those. So this problem is 3x plus 5, take away 4x, take away a -7. So that becomes 3x plus 5, take away 4x, take away a -7, which is +7. So this is -1x plus 12. Okay. 10 is true. This is just your distributive property twice. If you do those 4 multiplications, and put your middle term together with your outer term, you'll get -10x in the middle, 8x squared for 4x times 2x, and -3 for 1 times -3. The last one is a division problem with a common denominator, so that denominator of x belongs to both of the terms in the numerator. It's not multiplication in the numerator, it's addition. When you have addition and subtraction, the only way you could have gotten this single fraction, this is a single fraction, would have been to add two fractions with the same denominator. So this x belongs to x squared, and the x belongs to 5x. They share it. If you want to then take each one of these individually and reduce them, this becomes x to the first power because that x cancels with one of the x's on top, and this x cancels with that. Oh, it says x squared. Oh, thank you. Oh, you're right. I didn't even notice that square. Thank you. I only saw x plus 5. Okay, yes. I was looking at your answer saying, yeah, that's right, x plus 5. Yep, x plus 5. Okay, so what's the mistake when someone says x squared plus 5 or x plus 5x? Is they take this x and they cancel it into just one of these on top. Okay, and in order to cancel it, it has to go into everything on top. And another way to see that is to factor the numerator by taking x out as a common factor. You see? Now you have a foo-foo, a fancy form of 1 right there. X over x is 1, and 1 times x plus 5 is x plus 5. That's just another way to do it. All right, now notice, look, in general, we're not going to be covering 4 sections in one class. This is all prerequisite material, so that's why it's going to feel like a lot, and it's going to feel overwhelming today because you've got a lot of review material today. That's why we're giving you a week to do this homework, okay? So you need to focus on the areas that you feel weaker on and fly through the other stuff. I mean, maybe some of you feel really very good with multiplying 2 binomials, and so do that homework first. If you need a little help with rational exponents, ask me or go to the studio or whatever, okay? So let's take a look at the teaching demo where we're going to cover some of these things in a little more detail. And then you'll have about 10 or 15 minutes left to work on the class activities. Okay. What would make that first problem easier to look at and not get nervous about? Huh? Take a third of everything. Okay, a third of everything, if you would allow me to do what you said, Ramses, would look like this. This would be a third of everything is when I divide something by 3, okay? We don't want to do that, but we do want to take a third of some things. Yeah, what's that called? Cube root, okay? So first of all, my question was, do you like seeing things like fractions for the exponents? No, they kind of make you feel a little queasy, right? So if this was something like a square or a cube, how would you do it? Make the problem easier just for a minute, just on your eyes. So make this square. How would you do it if that was a square? What would you do? Nope, if it's a square. You double it. What do you double? Okay, I'm hearing lots of different answers. I'm hearing answers like this, double everything, so double everything. That's what I just heard someone say in front. I heard someone else say, do something with the 2 and FOIL it. FOIL applies to binomials and trinomials, polynomials, which means you have to see addition and subtraction. Do you see any addition and subtraction in those parentheses? No. To factor it, you have to find a common factor to everything, or you have to start with a polynomial, which you don't have. You'd multiply it by itself how many times? You multiply it by itself one other time, or you have 2 factors. Yes. Okay. So this is what it means. And you do it again. Now, some of you might mean, well, that's what I meant when I said double. But when you double, you multiply by 2, right? So we've got to be careful with our language. So what does this say? It says 64 times 64 times x to the 300 times x to the 300 times y to the 600 times y to the 600. And 64 times 64 means 64 squared, right? X to the 300 times x to the 300 is x to the 600. And y to the 600 times y to the 600 is y to the 1200. Okay? So this is the exponent property you're using. You're taking a product, nothing to do with FOIL, it's all multiplication, and you're raising this entire multiplication problem to that exponent. And the short way to do this is the longer way. And it's fine to do it the longer way if you don't know how to do it, is you apply that exponent to each one of your factors. So you square the 64, you square the 300 and x to the 300, and you square y to the 300. So if you do this out using this property of exponents, it looks like this. Okay? And I don't know what 64 squared is, so I'm just going to leave it at 64 squared. And then this involves another property of exponents. Either do it out like this if you forget the property, but 300 plus 300 is the same as two 300s, right? So you double this exponent. When you have a power raised to another power, you multiply. So this is x to the 600. This is y to the 1200. Okay? So you've just used two properties. These are the two properties we just used. We first applied the exponent to all of the factors, and then we had a power to a power here, and we multiply. Okay. So what was the little acronym I did? Oh, so I don't know if Ian taught you this, but Ian is really big, for those of you who had Ian last semester, on little memory devices. So for this, you know, it sounds silly, but it really worked for some students. When you have a multiplication problem raised to a power, I'm thinking, all I could think of, you know, I'm kind of a 60s, early 70s person. Power to the people was a big slogan back then. I'm like, power to the people. There's a power, but power to the people, power to the product. It's a product, but people aren't going to remember products. They can't even remember what that means. And I'm like, well, it applies to products and it applies to division problems. So instead of people, I call it power to the multi-dudes, right? Whenever you're multiplying, the power applies to the multiplication, and the power applies to division. So power to the multi-dudes covers two of your exponent problems. If it works for you, it's great. If it doesn't, I'm sorry. So now we're still back here. So what's going to happen to that 1/3 power? How can I write it out? So I'm going to apply the cubed root to that, because that's what one. Yeah, isn't that what I'm doing? Right? Why do I have to put it in archaic radical form? Isn't that doing the same thing? I'm applying the cubed root to each one of these, right? I just used my multi-dude exponent property. It's an exponent. Why convert it to a radical? It's not going to make it any easier. So this says the cubed root of 64, which is 4. 300 to the 1/3. What do you do to those two powers? You multiply. So you are taking 1/3 of something. There you go, Ramses. All right, you're taking 1/3 of each of the exponents, and you're all done. Okay? There's a lot there. We just covered a lot. Now, if you're weak with exponent properties, you want to pay attention to section P2, which is exponents. Radicals are exponents. That's P3. So if you're weak with your exponents, you're probably a little weak with your radicals. Rational exponents, students always forget, that's B. Lots of ways to do this problem, folks. I'm going to show you two. I'm going to show you the quickest way first. 8 can be written as 2 cubed. That's 8. 2 times 2 times 2. Now I have a power to a power. What do I do to those exponents? I multiply them. Boom, boom. 2 to the negative 2 says square 2, 4, and put it downstairs. There's your answer. That's one way to do it. Most students don't think about doing it that way. Okay, the other way to do it is to tear apart what each one of these pieces of the exponent means. This says to take the cubed root of 8 and I'm going to do it in this order. I always want to make my number as small as possible. So I'm always going to take my root first. I'm going to go to the cellar, to the denominator, the root cellar. Roots are in the cellar, right? If you grew up in a farm family, you put your potatoes, your carrots, everything in the cellar. Okay, that says to square it. And this says take the reciprocal, which just means change my position. It's a positional change. If you're in the numerator, you go to the denominator. If you're in the denominator, you go to the numerator. So I take my cubed root first. So if I'm using an equal sign, I got to be careful. If I take my cubed root first, I get 2. The cubed root of 8 is 2. I have negative 2 left. Now I square it, 2 squared, and then I have my negative 1 left, because negative 1 times 2 is negative 2. And that just says put me in the denominator. So that's how you do your rational exponents. Okay, we covered this. You did fine. I'm not going to cover C. Factoring. The most important thing about factoring is finding the greatest common factor. You always forget that as your first factoring technique. So I always told my 096 students to literally write GCF on their palm. I would let them bring that in as a little cheat sheet, you know, for anything, GCF, because if you forget it, you're going to look at it and say, how the heck do I do this? So the greatest common factor to both of these terms, first of all, factor here is a verb. It's not a noun. It's an action you're performing. You're going to take this subtraction problem and you're going to change it into a multiplication problem by saying that the factors of 5 and the factor of x belong to each one of those terms. I see a 5 in each term and I see an x. If I divide 5x into the first term, I would be left with x squared. And if I divide 5x into 45x, I'd be left with a 9. I have 45x. If I divide it by 5x, I have a 4 more 1. It's all right. 9x. 9 times 1 is 9. Okay. Now, some of you might think, hey, I just sweated and did that. I'm done. You're not done, because you can still factor. This is called the difference between two perfect squares. So you can factor that into two binomials, x and x, 3 and 3. And what do you know about the operations? They have to be opposite because the middle term is 0. So now you're done. All right. To reduce anything to lowest terms, folks, you can only reduce by dividing by a factor of 1. So right now you have 3 different pieces in the numerator, and guess what? That denominator would, to get this single fraction, I would have had x squared over this plus 3x over that minus 10 over that. That's the only way I could smush them together into one fraction. So you have absolutely no right to start stealing pieces from the denominator and canceling them with the pieces in the numerator. They're all addition and subtraction. The only way you don't change something in mathematics is if you multiply by 1 or divide by 1. So you have to factor both the numerator and denominator. You have to factor that, and you have to factor that. Recharge headset. I can't right now. Thank you. She's talking to me. Okay. So factors of 10 that differ by 3 is how I do this. Factors of 10 that differ by 3. What are the factors of 10 that differ by 3? 5 and 2. So I do x and x, 5 and 2. And now I say which one gets the plus, which one gets a minus. I look and see that that's a plus. So the 5, which is the bigger number, has to come after addition, and the 2 gets a subtraction. Okay. What's this one say? Factors of 8 that differ by 2. What are the factors of 8 that differ by 2? 4 times 2, right. So I go, you can always use the top to help you. Because if it's going to reduce, it would have to have x minus 2 in it. And it does. Here's your fancy form of 1. You can divide that out. You call it slashing. And there's your answer, x plus 5 over x plus 4. Right? I would suggest that you keep that in parentheses because you can fall to the evil temptation. When you don't put the parentheses, people do this. Cancel the X's. These are totally different numbers. There's no ones there. The only way you could cancel, the only way you could do this is if you wrote it. There's no way. No. If you had 5x over 4x, then you could cancel your x's. All right, I want you to get going. I'm gonna show you how to do this. I want you to get going on your class activities. No, folks, your class activities, there's quite a few of them. Give yourself a couple of days to do them. While you're in class, right, would you prefer me to go over this last one, or you want to start this? Do you have a feeling of what you want? Do you know how to add two fractions like this? This would have been the last thing you had in 096. You're okay with that? All right, so I'll just write it up for the notes, and you can, why don't you work on the thing you think you'll have the most difficulty with, so you can ask me if you need help. How do you ask for help in the class? You raise your hand, or you put up that flag that's right on your desk. See that flag? That's how I know to go from one table to the other.